Our Sun is a cosmic lightweight. It seems immense to us, but in the grand stellar menagerie, it is barely a footnote. This journey explores 25 facts about the universe's true titans, stars so massive they defy belief. You will discover how these monsters are born, why they live in a constant state of furious rebellion, and how their spectacular deaths forge the very elements that make up our world. We will uncover why some of these giants seem to vanish without a trace, and how their final moments can unleash beams of energy capable of sterilizing entire galaxies. What cosmic spectacle comes to mind when you think of ultimate power? To put that into perspective, our Sun is classified as a yellow dwarf star. That term might sound unimpressive, but it is the steady, reliable engine of our solar system, a sphere of plasma over 860,000 miles wide. Yet in the hierarchy of stars, it is utterly ordinary. To find the true giants, you must look to a different class of stars altogether, the hypergiants and supergiants. These are the cosmic skyscrapers, the leviathans of light. Consider Scuti, a red supergiant located in the constellation Scutum. Its radius is estimated to be over 1,700 times that of our Sun. If you could place our Sun at the center of Scuti, its surface would lie somewhere between the orbits of Jupiter and Saturn. The sheer volume is incomprehensible. You could fit over 5 billion suns inside it. An even more extreme candidate is Stephenson 218, a red supergiant whose estimated radius might surpass even that. So let us use a simple analogy. If our familiar, life-giving Sun were the size of a garden pea sitting on a table, a star like Scuti would not be a marble or a golf ball. It would be a colossal beach ball towering over that tiny pea. And the very largest of these hypergiants would be the size of a small car, completely dominating the room. This is not just a difference in size, it is a difference in cosmic category. These stars occupy a realm of physical extremes where the normal rules of stellar existence are stretched to their absolute breaking point. Such staggering size demands an equally dramatic origin story. These cosmic giants are never born alone in some quiet corner of the galaxy. They emerge from the most crowded and chaotic stellar nurseries imaginable, vast clouds of gas and dust like the famous Orion Nebula. These nebulae are cosmic cradles, but they are not peaceful. Within their dark, swirling depths, gravity begins to pull clumps of material together. For a star like our Sun, this is a relatively slow and gentle process. For a future hypergiant, it is a frenzy. Enormous rivers of gas, thousands of times the mass of our entire solar system, rush inward in a violent gravitational collapse. The core that forms is not just a spark, it is a sudden, furious inferno, a protostar accumulating material at a breathtaking rate. This rapid feast of gas and dust is what allows it to reach such incomprehensible bulk so quickly. The birth itself is a spectacle that reshapes its entire neighborhood. The intense radiation and powerful stellar winds from the newborn behemoth blast away the remaining gas, carving out vast cavities and lighting up the nebula from within. In doing so, this violent toddler often compresses the surrounding gas clouds, triggering a chain reaction and forcing new stars to form around it. A single massive star does not just enter the universe quietly. It announces its arrival by sculpting the nebula and igniting the birth of its own stellar siblings. This chaotic beginning sets the stage for a life lived on the edge, a constant and desperate struggle. Their furious birth is only a prelude to a life of impossible intensity. This is the great cosmic trade-off for such immense power. A star's mass dictates its lifespan, and for these giants, the price of their brilliance is a shockingly short existence. Our steady Sun, for all its importance to us, is a model of stellar frugality. It fuses hydrogen into helium in its core at a careful, measured pace. a process that will sustain it for roughly 10 billion years from birth to its quiet end as a white dwarf. For a star just 20 times more massive, however, the story is radically different. Its lifespan plummets to a mere 10 million years, that is 1,000 times shorter. If the Sun's entire life were stretched across a single calendar year, a star 20 times its mass would blaze into being and vanish all within the span of 3.5 days. Why such a drastic difference? It all comes down to the relentless pressure at the star's heart. A massive star's core is an unimaginable crucible of heat and density, far more extreme than our Sun's. This creates a furnace that burns its nuclear fuel not with a steady glow but with a desperate, roaring fury. It must fuse hydrogen at a staggering rate, not out of choice but out of sheer survival. The star's own incredible gravity is constantly trying to crush it inward, and the only thing holding that collapse at bay is the outward pressure generated by the nuclear fusion in its core. So the more massive the star, the stronger its gravity, and the faster it must burn its fuel to keep from imploding. It is a race it is destined to lose. This furious consumption means it tears through its available hydrogen in a cosmic blink, living a life that is spectacularly brilliant, violently unstable, and tragically brief. Its entire existence is a constant, high-stakes rebellion against its own self-destruction. This frantic burning is not the same process that powers our Sun. Deep within a star like ours, fusion happens through the relatively slow and steady proton-proton chain, where hydrogen nuclei directly combine to form helium. It is a fundamental process, but for a true titan, it is not nearly efficient enough. To withstand its own crushing gravity, a massive star must switch to a far more powerful engine, the carbon-nitrogen-oxygen cycle. Think of it this way: if the proton-proton chain is a dependable campfire, the CNO cycle is an industrial blast furnace. This process uses carbon, nitrogen, and oxygen atoms already present in the star's core as a kind of nuclear catalyst. They act as intermediaries, helping to fuse hydrogen into helium at a dramatically faster and more temperature-sensitive rate. The key word is sensitive. The power output of the CNO cycle skyrockets with even a small increase in core temperature. This creates a runaway feedback loop. More mass means higher core temperature, which triggers vastly more efficient fusion, which releases even more energy, heating the core further. It is a self-amplifying cycle of stellar overdrive. This allows the star to momentarily hold its immense weight aloft, but it also means it consumes its nuclear fuel at a breathtaking, unsustainable pace. The star does not stop at helium. As the hydrogen in its core depletes, the furnace adapts. Gravity squeezes the core tighter, raising the temperature again until a new chapter of fusion can begin. Helium atoms now fuse into carbon, then carbon fuses into neon, neon into oxygen, oxygen into silicon. Each new fuel burns faster and hotter than the last. The star's final days become a frantic, layered sprint. It is like a machine shifting into ever higher gears, each one more violent and short-lived than the last, all leading toward one inevitable element: iron. This is where the race ends. Fusing iron does not release energy, it consumes it. When the star's core finally becomes iron, the furnace sputters and dies. In that instant, the outward pressure that has supported the star for millions of years vanishes. The entire structure, a colossal onion with layers of different elements, has nothing left to hold it up. What happens next is the ultimate cosmic collapse, a prelude to an explosion so powerful it can outshine an entire galaxy. Iron is the final, fatal element forged in that frantic sprint. The star's core, now a ball of inert iron, has reached the end of the line. For a fleeting moment, there is a perfect, terrifying silence at the heart of the giant. The fusion furnace that has roared for millions of years suddenly goes dark. With no outward pressure left to resist it, the star's own immense gravity wins its ancient war in an instant. The core collapses not in a slow fall, but in a violent, catastrophic implosion. In less than a second, a core the size of Earth is crushed into a sphere of ultra-dense neutrons barely the size of a city. This sudden collapse releases a staggering shockwave of energy that blasts outward through the star's layered interior, tearing through the shells of silicon, oxygen, neon, carbon, and helium in a furious wave of destruction. The entire outer structure of the star, a colossal sphere that could have engulfed the orbit of Jupiter, is violently ejected into space in one of the most energetic events in the cosmos, a supernova. For a few weeks, this single dying star can outshine the combined light of every other star in its entire galaxy. This is the final, spectacular act of a massive star, an explosion that scatters the newly forged heavy elements like carbon, oxygen, and iron across the interstellar medium, seeding future generations of stars, planets, and ultimately life itself. But what remains after the light of the supernova fades? The collapsed core endures. Depending on its initial mass, it can become one of two of the universe's most bizarre and extreme objects, a neutron star or a black hole. The supernova is not the only way a massive star shapes its surroundings. Long before its final cataclysm, it is constantly reshaping the galaxy with a relentless, invisible force, its stellar wind. This is not a gentle breeze. The radiation pouring from a hypergiant surface is so intense that it physically blasts the star's own outer layers into space, creating a supersonic gale of charged particles. The scale of this loss is almost beyond comprehension. While our Sun sheds a minuscule trickle of solar wind, a star like Eta Carinae, one of the most massive and unstable stars known, can eject over 100 times the mass of Earth every single year. That is the equivalent of an entire planet's worth of material, not in a single explosion, but in a continuous, furious exhalation that lasts for millennia. These winds travel at millions of miles per hour, and they act like a cosmic sandblaster on the surrounding space. Where the star sits within a vast cloud of gas and dust, its wind carves out a gigantic cavity, pushing the interstellar material outward into a delicate, glowing shell. We see the breathtaking results as nebulae with names like the Bubble Nebula. That beautiful, seemingly fragile sphere of gas over 7 light-years across is not a remnant of an explosion. It is the ongoing work of a single, ferociously windy star at its center, literally blowing a bubble in the fabric of the galaxy. This sculpting has profound consequences. By compressing the gas at the edges of these bubbles, the stellar winds can trigger the collapse of new clouds, forcing the birth of the next generation of stars. In this way, a massive star becomes an architect, its destructive winds paradoxically giving rise to stellar nurseries and sculpting the beautiful structures we admire through our telescopes, all while it slowly erodes itself away in the process. This self-destructive wind creates one of the greatest puzzles in stellar astrophysics. How can a star be so massive yet so determined to tear itself apart? The process is not always a steady stream. For the most extreme hypergiants, mass loss becomes a violent, erratic series of eruptions. No star demonstrates this better than Eta Carinae, a chaotic binary system whose primary star contains well over 100 times the mass of our Sun. In the 1840s, it underwent what astronomers call the Great Eruption. For over 20 years, it became the second brightest star in the night sky, not because it was dying in a supernova, but because it was violently expelling its own outer layers in a titanic outburst. It ejected at least 10 times the mass of our Sun in that single event, forming the vast bipolar homunculus nebula we see around it today. That eruption was not its final death throes. It was a stellar temper tantrum that happened over 170 years ago, and the star is still there, unstable and unpredictable. This extreme, episodic mass loss completely rewrites the star's life story. By violently stripping away its hydrogen-rich outer envelope long before the core is ready to collapse, it can prematurely expose the hotter, deeper layers of helium and heavier elements. This can transform a star that should have died as a red supergiant into something else entirely, perhaps a much hotter, bluer, and more unstable Wolf-Rayet star, shrouded in its own ejected gas. The star's ultimate fate, whether it becomes a neutron star or a black hole, and the power of its final supernova, all depend on how much mass it manages to shed in these chaotic final chapters. Because this process is so violent and irregular, it makes predicting the life and death of these stellar titans incredibly difficult. Each one seems to follow its own unique, tumultuous path to destruction. This frantic, layered fusion does more than just power the star. It performs the universe's most essential alchemy. Every element in your body, in the ground beneath your feet, and in the screen you are looking at right now, originated from a process that can only occur under the extreme conditions found within a massive star. Our Sun, for all its importance, is a relatively modest chemist. It primarily fuses hydrogen into helium, and near the end of its life, it will forge carbon and a little oxygen. But that is where its capabilities end. To create the heavier, more complex atoms that build rocky planets and living things, you need a far more powerful forge. The core of a massive star provides that. As the star burns through each fuel, the ash of one fusion stage becomes the fuel for the next. Helium fuses into carbon. Carbon atoms then collide under immense heat and pressure to form neon and magnesium. Neon burning produces oxygen and more magnesium. Oxygen burning creates silicon and sulfur. Finally, silicon fuses into iron. This step-by-step nuclear cooking, layered like the rings of an onion, builds the periodic table from the inside out. It is a cosmic production line where each stage operates at a higher temperature and concludes more quickly than the last. The silicon to iron stage, for instance, might last less than a single day in a star's multimillion-year life. All of this frantic activity is locked inside the star until its final, violent death. The supernova explosion does not just destroy the star, it completes the factory's work. The unimaginable energy of the blast provides the conditions to forge elements even heavier than iron, like gold, silver, platinum, and uranium, through rapid neutron capture. Then it scatters this newly minted periodic table across space. So the calcium that strengthens your bones, the iron that carries oxygen in your blood, and the silicon that forms the bedrock of continents, all were forged in the heart of a massive star that died billions of years ago. That gold ring or necklace is quite literally a piece of a stellar explosion, a remnant of cosmic violence worn as jewelry. We are all, in the most profound sense, made of stardust, the recycled remains of these ancient giants. That final, furious forge is the supernova itself. The instant the iron core collapses, the shockwave it unleashes does more than just tear the star apart. It creates a temporary environment of almost unimaginable violence, a cauldron of energy so intense it becomes the only place in the universe where certain elements can be born. This is where the story of our stardust gets its final, crucial chapter. While the layered fusion inside the living star built elements up to iron, everything heavier requires a different process, one that cannot happen under normal stellar conditions. Fusing iron actually consumes energy. It would make the core collapse faster. So how do we get gold, silver, platinum, or uranium? The answer is a frantic scramble in the heart of the explosion called the R process, which stands for rapid neutron capture. In the maelstrom of the collapsing core and the outgoing shockwave, a flood of free neutrons is created. Atomic nuclei, the seeds of lighter elements, are bombarded by this dense neutron storm. They capture these neutrons faster than they can naturally decay, bulking up into extremely heavy, unstable versions of themselves. These overweight nuclei then undergo radioactive decay, settling down into the stable, heavy elements we recognize on the periodic table. This entire sequence from capture to decay happens in a matter of seconds. Think of it as the universe's most extreme and fastest assembly line. Normal fusion is like carefully welding atoms together. The R process is like throwing an avalanche of parts at a framework and hoping a finished truck comes out the other side. And it only works in the most violent events we know, the core collapse of a massive star or the collision of two neutron stars. The supernova then does the essential delivery work. Its explosive force flings these newly minted heavy elements, along with all the carbon, oxygen, and silicon forged during the star's life, out into the interstellar void at thousands of miles per second. This enriched material mixes with clouds of primordial hydrogen and helium, becoming the raw ingredients for the next generation of stars and planets. Our own solar system formed from a cloud that was peppered with the debris of countless such explosions. So the iron in Earth's core, the gold in a bank vault, and the iodine in your thyroid, all were manufactured in those few seconds of apocalyptic stellar death, billions of years ago and light years away. We are not just made of stardust, we are made of supernova dust, the ashes of the universe's most spectacular furnaces. The aftermath of that cosmic explosion leaves behind a ghost, the collapsed core of the star. Its fate depends on a single critical number. The mass that remains after the supernova has blasted everything else away. There is a fateful divide in stellar physics, a threshold often estimated around 20 to 25 times the mass of our Sun. For a star whose leftover core falls below this line, the collapse is halted by a bizarre force of quantum physics. When protons and electrons are crushed together with unimaginable pressure, they merge to form neutrons. The entire core, once the size of Earth, becomes a single city-sized ball of this ultra-dense neutron matter. This is a neutron star. A single teaspoon of its material would weigh billions of tons on Earth, a mountain range compressed into a sugar cube. It spins furiously, often hundreds of times per second, and possesses a magnetic field trillions of times stronger than Earth's. But for a star whose core remains above that critical mass limit, something far stranger occurs. No known force in the universe is strong enough to stop the collapse. The gravity is simply too overwhelming. The core continues to crush inward past the neutron star stage, past any conceivable form of matter. It shrinks to a point of infinite density, a singularity. Around this point, the gravity becomes so intense that it warps the fabric of space and time itself, creating a boundary from which nothing, not even light, can ever return. This is the event horizon of a black hole. The most massive stars, therefore, leave behind the universe's most extreme and enigmatic remnants. One is a dying ember of unimaginable density, a pulsating beacon. The other is a tear in reality, a one-way door out of our universe. The legacy of a giant is either a city of neutronium or a silent, dark prison from which nothing escapes. These stellar titans rarely live in solitude. In fact, the vast majority of massive stars are born with at least one companion, locked in a gravitational dance that can twist their destinies into something even stranger. Picture a cosmic waltz where one partner is a giant 100 times heavier than our Sun, and the other is a more modest Sun-like star. They orbit a common center of gravity, sometimes over periods of many years. But in tighter, more intimate binaries, the dance becomes a desperate struggle for survival. The sheer gravitational pull of the massive star can begin to siphon the atmosphere directly off its smaller companion. Rivers of hydrogen gas stream across the space between them, swirling into a glowing disk of stolen material before crashing onto the surface of the hungry giant. This process, called mass transfer, dramatically alters the life story of both stars. The massive star gorges itself, potentially gaining even more fuel and mass, which can make its eventual explosion even more powerful. Meanwhile, the donor star is stripped down to its hot, dense core, prematurely transforming it into a bizarre, helium-rich star. Their fates become forever intertwined, a stellar partnership that turns parasitic. Yet this is only the beginning of the strangeness. Imagine a system where one of these binary partners has already met its end. The massive star explodes in a supernova and its core collapses into a neutron star or a black hole. What remains is a system almost beyond belief, a living, breathing massive star orbiting the corpse of its former sibling. In these extreme binaries, the dead star's immense gravity can pull a continuous stream of gas from its living companion. As this material spirals at near light speed into the neutron star or plunges past the event horizon of the black hole, it heats to millions of degrees and screams out in X-rays. From Earth, we see these as flickering, powerful X-ray sources, the death cry of stolen stardust, and this too is a temporary state. The dance is slowly decaying. As they orbit, such a system loses energy in the form of ripples in spacetime itself, gravitational waves. Over millions of years, these ripples cause the stars to draw closer and closer, tightening their fatal embrace until finally they collide. That merger between two neutron stars or a neutron star and a black hole is what our detectors like LIGO have felt shaking the fabric of the universe. So a massive star's companion can be its meal, its murderer, or the source of its final, universe-shaking collision. One of the most vivid examples of this cosmic theft is a system known as a high-mass X-ray binary. Here, the vampire is not a star but a stellar corpse. Picture a massive blue supergiant, tens of times heavier than our Sun, locked in a tight, frantic orbit with a tiny, city-sized neutron star. The neutron star may be small, but its gravity is unimaginably strong. That immense pull creates a relentless tidal force, literally tearing the outer atmosphere away from the living supergiant. A torrent of hydrogen and helium gas does not simply fall inward. It gets whipped into a frenzied, glowing whirlpool around the neutron star called an accretion disk. As this stolen stellar material spirals down at nearly the speed of light, it is compressed and heated to temperatures of millions of degrees. It is in this searing maelstrom that the system screams its presence across the galaxy, not in visible light but in high-energy X-rays. From our vantage point, we see a regular, pulsing beacon of X-rays flashing on and off as the neutron star spins, its lighthouse beam of radiation sweeping past us with each rotation. This vampirism has profound consequences for both objects. For the neutron star, the influx of fresh hydrogen fuel can actually restart nuclear fusion on its scorched surface, leading to violent thermonuclear explosions we detect as X-ray bursts. It is a monstrous form of rejuvenation, briefly reanimating a dead star with the lifeblood of its companion. For the massive donor star, however, this is a slow death sentence. It is being systematically drained, its outer envelope stripped away. This process can prematurely expose its hotter, helium-rich core, radically altering its evolution and hastening its own collapse. In this lethal dance, one star feeds on the other to briefly cheat death, while the other is consumed to fulfill a destiny it never would have met alone. This cosmic vampirism is just one way a massive star's life becomes chaotic. Another lies within the star's own unstable heart. Not all giants burn with a steady flame. Some exist in a state of perpetual, rhythmic upheaval, throbbing like a cosmic heartbeat. This occurs in a special region of stellar evolution astronomers called the instability strip. Here, stars do not simply shine, they pulsate. They are not stable balls of plasma, but colossal breathing entities, expanding and contracting over periods of months or years. The most dramatic examples are the yellow hypergiants, rare and temporary monsters caught in a volatile transition. A star like Rho Cassiopeiae, thousands of light-years away, is a textbook case. It is a sun so vast it could engulf the orbit of Jupiter, yet it is not content to simply exist. Deep within its layers, helium is being ionized, stripped of its electrons. This process acts like a powerful energy sponge, trapping radiation and causing pressure to build. When the pressure reaches a critical point, the entire outer envelope of the star violently expands, cooling as it grows. Then the trapped radiation finally breaks free, the pressure drops, and gravity pulls the colossal atmosphere crashing back inward, reheating it. This cycle repeats, a slow, monstrous breath. With each expansion, the star cools and reddens. With each contraction, it heats and turns more blue-yellow. From our vantage point, its brightness can change by a factor of 4 or more, flickering unpredictably in the night sky. Sometimes the pulsation grows so violent that the star cannot contain itself. Instead of gently settling back, it ejects an entire shell of its own atmosphere into space in a titanic stellar sneeze. Rho Cassiopeiae did exactly this around the year 2000, blasting away a chunk of material with 10,000 times the mass of Earth. These stars are walking a tightrope, and each pulsation, each eruption, brings them closer to the edge of total collapse. They are not just dying stars, they are dying stars that are actively, visibly coming apart at the seams, offering us a front-row seat to stellar instability on a scale that is almost beyond imagination. But even the catastrophic fury of a supernova is not the final word on stellar destruction. For the very largest of these giants, those born with over 40 times the mass of our Sun, death arrives in an even more spectacular form, a hypernova. This is a supernova dialed up to an apocalyptic extreme. The core collapse is so violent and the energy release so immense that it outshines an entire galaxy not for weeks but for months. The physics behind it is a step beyond the ordinary. In these ultra-massive stars, the collapsing iron core is so heavy that it cannot even stabilize as a neutron star, not even for an instant. It plummets directly into a black hole. As it falls, vast amounts of material swirl around this newborn singularity in a disk of superheated plasma, and magnetic fields trillions of times stronger than any magnet on Earth channel some of the infalling matter into two narrow, opposing jets. These jets, composed of particles accelerated to over 99.9% the speed of light, blast their way out through the star's outer layers and scream into interstellar space. And it is here, in these relativistic jets, that we find the signature of the universe's most powerful explosions since its birth, gamma-ray bursts. When one of those jets is pointed directly at Earth, we witness a long-duration gamma-ray burst, a flash of gamma radiation so intense it briefly outshines every other source of gamma rays in the cosmos. For those few seconds, it releases more energy than our Sun will emit in its entire 10 billion-year lifetime. The beam is so focused, so concentrated, that it carries the star's final scream across billions of light years. The implications are terrifyingly real. If a star within our own galaxy, say a few thousand light years away, were to collapse into a hypernova and one of its jets were aimed at our solar system, the consequences would be apocalyptic. That narrow beam of high-energy radiation would not just light up our sky, it would strike our atmosphere like a cosmic blowtorch. It would strip away the ozone layer, trigger intense chemical reactions creating toxic smog, and bathe the planet in deadly radiation. Such an event is thought to be a possible cause for some of Earth's mass extinctions in the deep past. A nearby gamma-ray burst would not just end life on Earth, it could sterilize planets across an entire sector of the galaxy, a reminder that the universe's most brilliant lights are also its most dangerous. The collapsar model provides the terrifying blueprint for this ultimate stellar catastrophe. At its heart is a star not just massive, but also spinning rapidly like a cosmic top. When its iron core reaches the point of no return, it does not form a neutron star as a brief stopping point. Instead, its immense mass and angular momentum cause it to plunge directly into oblivion, birthing a black hole almost instantaneously. But the star's story does not end with that silent singularity. An enormous amount of stellar material, the outer layers that have not yet felt the collapse, still surrounds this newborn void. Drawn inward by its irresistible gravity, this doomed matter does not fall straight in. The star's rapid spin forces it into a frenzied whirlpool, a superheated accretion disk spinning around the black hole at nearly the speed of light. Temperatures in this disk soar to billions of degrees, creating a maelstrom of plasma and radiation. Within this chaos, something extraordinary happens. Intense magnetic fields, wound up by the furious rotation, channel some of the infalling material. Instead of spiraling into the black hole, this plasma gets focused and accelerated outward along the star's rotational axis, erupting from its poles in two narrow, opposing jets. These are not gentle streams, they are beams of pure energy and matter moving at over 99.9% the speed of light. They act like cosmic blowtorches, drilling their way up and out through the star's remaining body. It is this final, desperate escape act that we witness across the universe. When one of those ultra-focused, relativistic jets happens to be pointed directly at Earth, the intense gamma radiation produced as it punches through the stellar debris reaches our telescopes as a long-duration gamma-ray burst. For those few seconds, we are staring directly into the beam of a cosmic lighthouse, a beacon that signals not a safe harbor, but the birth of a black hole from the corpse of a star. This predicted abundance of red supergiants simply does not match what we see in our telescopes. It is as if a whole generation of stars vanished from the cosmic census, creating a nagging puzzle known as the red supergiant problem. According to our best models, a star between about 8 and 25 solar masses should spend its final million years as a bloated, cool red supergiant, a phase that should be relatively easy to spot. Yet when astronomers survey nearby galaxies like the Large Magellanic Cloud, they find far fewer of these crimson giants than expected. Where did they all go? One compelling possibility is that the stars themselves are cheating, skipping a step in their own life cycle. For the most massive and unstable stars, their self-destructive stellar winds might be far more efficient than we thought. Imagine a star shedding its outer hydrogen envelope not in a steady stream, but in violent, episodic eruptions like the Great Eruption of Eta Carinii. If it strips this envelope away fast enough, it could prematurely expose its hotter, helium-burning core before it ever has a chance to cool and expand into a classic red supergiant. The star would effectively transition from a blue giant directly to a hotter, more exotic Wolf-Rayet star, cloaked in its own ejected gas, bypassing the red phase entirely. Another, more dramatic theory suggests a far quieter exit. Perhaps a significant fraction of these stars do not announce their deaths with a brilliant supernova at all. Instead of the core collapse triggering a shock wave that blows the star apart, the entire star might simply implode. In this failed supernova or unnova scenario, the star's core collapses directly into a black hole, and the overlying stellar material falls inward after it. With no powerful shockwave to heat and light up the ejector, there is no brilliant flash to signal its passing. The star would simply wink out of the sky, leaving behind only a dark remnant. This silent disappearance could explain both the missing red supergiants and why we observe fewer core collapse supernova than we predict. It is a humbling reminder that even for stars, death does not always come with fireworks. Sometimes the universe's most massive objects simply vanish into the dark, taking their final secrets with them. Their silent disappearances are a cosmic mystery, but their collective impact is undeniable. To understand a galaxy's life story, you must look to its most massive stars. These giants are not mere inhabitants, they are the primary architects, the engines of galactic ecology. From birth to death, they inject energy, motion, and raw material into the vast interstellar medium, shaping everything around them. It begins with their fierce ultraviolet radiation. A single O-type star, many times hotter and brighter than our Sun, emits a torrent of high-energy photons that rip electrons from atoms in surrounding gas clouds. This process, called ionization, creates vast glowing bubbles of plasma known as H2 regions, like the magnificent Orion Nebula. These are not just beautiful cosmic clouds, they are stellar nurseries being sculpted and illuminated by the very stars they recently birthed. The intense radiation pressure and powerful stellar winds physically push on the surrounding gas, compressing it into dense shells and pillars. In some places, this compression triggers the collapse of new clouds, sparking another round of star formation. In others, the winds are so violent they blast the gas away entirely, shutting down star birth in that region for eons. A massive star is a regulatory force, a cosmic gardener that both plants new seeds and clears whole fields with its furious breath. This cycle of creation and destruction dictates the rhythm of star formation across a galaxy's spiral arms, determining where new suns will ignite and where cosmic deserts will form. Their influence, however, does not end with their light or their wind. It culminates in their final, elemental gift. When a massive star explodes, it does more than just scatter stardust. The supernova shockwave slams into the surrounding interstellar medium at thousands of miles per second, like a titanic plow churning the galactic soil. It sweeps up vast amounts of gas, compressing it into new, dense, and turbulent structures that will eventually collapse to form the next generation of stars. Crucially, this new generation will be born from material enriched with the heavy elements forged in that explosion. Each cycle of massive star life and death raises the overall metallicity, the concentration of elements heavier than hydrogen and helium of the galaxy. The first stars in the universe, known as population 3 stars, were pure hydrogen and helium giants. Their cataclysmic death seeded the cosmos with the first metals. The stars that formed from that enriched debris, like our Sun, contained enough carbon, oxygen, iron, and silicon to form rocky planets and ultimately life. So the chemical evolution of a galaxy, from a primordial soup of light elements to a complex periodic table capable of building worlds like ours, is a direct product of its massive stars. They are the great recyclers, taking the simple ingredients of the early universe and, through their furious lives and violent deaths, transforming them into the complex chemistry of possibility. Without these stellar titans, galaxies would be dark, quiet, and chemically barren places, incapable of crafting the building blocks of planets or life. This galactic gardening on a grand scale creates structures of breathtaking size. When massive stars are not born alone but in dense clusters, their collective deaths can reshape the galaxy itself. Picture a stellar nursery like the Tarantula Nebula in the Large Magellanic Cloud, a cauldron where hundreds of giant stars are born together. They live their short, brilliant lives and then, one by one, they die. Each supernova explosion sends a powerful shockwave plowing into space. When these stars are clustered close together, their individual shockwaves begin to overlap and merge. They do not cancel each other out, they reinforce one another, pushing in the same direction like a coordinated team of cosmic bulldozers. Over millions of years, this relentless, combined force carves out a single, colossal cavity in the surrounding gas and dust, a structure astronomers call a superbubble. These are not small features. A single superbubble can stretch for hundreds of light years across, large enough to swallow thousands of solar systems. Its walls are glowing filaments of compressed gas, lit up by the intense ultraviolet radiation from the few remaining massive stars still shining inside. The interior of the bubble is not empty. It is filled with a thin, incredibly hot plasma, gas that has been heated to millions of degrees by the relentless barrage of supernova shocks. This hot gas has tremendous pressure and it wants to expand. In the dense plane of the galactic disk, it pushes outward, continuing to inflate the superbubble. But sometimes the pressure finds a weak spot. The combined energy of so many supernova can become so immense that it punches a hole straight through the galaxy's gaseous disk. The searing hot plasma from inside the superbubble erupts upward, blasting out into the much thinner halo of gas that surrounds the galaxy's spiral arms. This creates a spectacular phenomenon known as a galactic fountain. Enormous plumes of multimillion-degree gas, enriched with iron, oxygen, and silicon from all those stellar explosions, arc high above the galactic plane. They travel for thousands of light years into the halo, where they eventually cool, condense into clouds, and then, pulled by the galaxy's gravity, they rain back down onto the disk below. This is the galaxy's ultimate recycling program. The heavy elements forged in the hearts of massive stars are not just scattered nearby. They are lifted high into the galactic atmosphere and sprinkled back down across vast distances, seeding future generations of stars and planets with the essential ingredients for complexity. Our own solar system may have formed from a cloud of gas that was once part of such a cosmic downpour, enriched by the death throes of a stellar cluster we will never see. The universe's first dawn was not lit by stars like our own. Before galaxies, before planets, before any element heavier than helium existed, the cosmos was a dark, simple place, a vast sea of hydrogen and helium gas. From this pristine soup, the very first stars were born, and they were unlike anything that exists today. Astronomers call them population 3 stars, and their existence is one of the most profound hypotheses in all of cosmology. Without the dust and heavy elements that help modern gas clouds cool and fragment, the first stellar nurseries could only collapse into absolutely monstrous objects. Current theories suggest these primordial giants likely formed with masses ranging from 100 to over 1,000 times that of our Sun. Imagine a star so colossal it makes the hypergiants we see today look almost modest by comparison. These were the universe's first candles, and they ignited with a ferocious, pure light, ending the cosmic dark ages that followed the Big Bang. Their lives, however, were spectacularly short, burning through their pristine fuel at a breakneck pace. But their deaths were even more consequential. For the very largest of these first stars, their demise followed a script that no modern star can replicate, a process called a pair instability supernova. In their incredibly hot cores, the energy of gamma-ray photons became so intense that it spontaneously created pairs of electrons and their antimatter counterparts, positrons. This conversion of radiation into matter robbed the core of its outward pressure almost instantly. Without warning, the star's central support vanished. The result was not a core collapse followed by a rebound, but a total, runaway thermonuclear explosion. The entire star, from core to surface, would be utterly obliterated, leaving behind no black hole, no neutron star, not even a remnant. It was complete stellar annihilation. In that final, universe-shaking flash, these first giants performed the cosmos's most crucial act of alchemy. They fused the primordial hydrogen and helium into the first heavier elements carbon, oxygen, neon, silicon, and iron, and then scattered them into the void. This first pollution was the greatest gift. It seeded the early universe with the raw materials for everything to come. The dust for future planets, the oxygen for future water, and the carbon for future life. Every star that formed after, including our Sun, every rock, every living thing, carries within it atoms forged in those first catastrophic explosions. The age of the cosmic titans began not with a whimper, but with a blaze of light so violent it changed the fabric of reality itself. R136A1 is a staggering monster. Nestled in the heart of the Tarantula Nebula, this star is currently the heavyweight champion we know of, weighing in at over 250 times the mass of our Sun. Its existence seems to defy a fundamental rule of stellar physics. For decades, theorists have argued there must be a firm ceiling, an upper mass limit where a star's own fierce light becomes its destroyer. The logic is compelling. The radiation pouring from a star's core creates an outward pressure. For a star to be stable, this radiation pressure must perfectly balance the inward crush of its own gravity. But as you pile on more and more mass, the core burns hotter and brighter, and that radiation pressure grows exponentially. The theory suggests that around 150 to 200 solar masses, the radiation pressure would become so intense it would start violently ejecting the star's outer layers faster than new material could ever fall in. The star would effectively blow itself apart during formation, unable to reach a stable state. So how does R136A1 and others like it exist? The answer may lie in its frenzied birth within an ultra-dense cluster. It might have formed from the rapid merger of several large protostars in that crowded stellar nursery, a process that could allow it to bypass the usual formation limits and reach its colossal size almost instantly. Yet even this behemoth might not be the true king. Our view of the cosmos is still limited. The densest, most active stellar nurseries, like the very core of our own Milky Way, are often veiled by thick curtains of cosmic dust that visible light telescopes cannot penetrate. Could there be even more massive stars lurking in those hidden hearts, stars of 300 or even 400 solar masses, shrouded in their own natal cocoons? Furthermore, as we just discussed, the first stars in the universe are believed to have been pure hydrogen and helium giants of unimaginable scale. While those original titans are long gone, their potential descendants in the early universe might have pushed mass to levels we have never observed. This is where our next generation of eyes comes in. Instruments like the James Webb Space Telescope, with its infrared vision capable of peering through dust and looking back to the universe's first epochs, are actively searching. They are scanning those obscured stellar factories and the distant, early galaxies for the infrared signatures of true supergiants. It is entirely possible that the current record holders we catalogue in our nearby galactic neighborhood are merely the largest fish in our small, visible pond. The true leviathans may still be waiting in the cosmic shadows, their immense forms hidden by dust or lost to time, ready to be revealed by the telescopes of tomorrow and rewrite our understanding of stellar limits once again. This theoretical ceiling is known as the Eddington limit, a fundamental law of stellar physics. Every star exists in a delicate balancing act. The inward crush of its own immense gravity constantly tries to collapse it. The only thing holding that collapse at bay is the outward pressure generated by the radiation pouring from its core. The Eddington luminosity defines the precise point where these two titanic forces reach a perfect, stable equilibrium. For a star of a given mass, this is the maximum brightness it can achieve before the outward push of its own light overpowers gravity. Think of it as a star trying to hold up an increasingly heavy blanket with a beam of light. Make the light too bright and it blows the blanket clean off. For a star, that blanket is its own outer atmosphere. If a star's luminosity pushes past this critical threshold, the radiation pressure becomes so intense that it does not just support the star, it violently expels its outer layers into space. This creates a natural speed bump for stellar growth. A protostar trying to accumulate more mass would also grow brighter, and eventually that ferocious light would prevent any new material from falling in, effectively capping its size. This principle suggests there should be a firm upper limit to how massive a stable star can ever become, likely somewhere between 150 and 200 solar masses. Yet we observe stars like R136A1 that seem to break this rule. So what is happening? The answer lies in the fine print of cosmic engineering. The Eddington limit assumes a perfectly spherical, non-rotating star with a uniform composition. Real stars, especially the monsters, are messy, dynamic, and fast-spinning. Rotation can flatten them, concentrating heat and radiation at their poles and allowing them to retain more mass around their bulging equators. More importantly, their composition is not pure hydrogen. The presence of heavier elements, metals like iron, makes the stellar atmosphere more opaque. This opacity traps radiation more effectively, meaning the outward pressure builds up and acts more forcefully within the star's layers, not just at the surface. This allows a star to exist in a state of super-Eddington luminosity locally, in its deep interior, while its outer surface remains just stable enough to hold on. This is not a calm existence, it is a state of perpetual violent tension. A star like Eta Carinii is the ultimate demonstration of this precarious dance. It is almost certainly shining above the classical Eddington limit for its mass. The result is not stability, but the catastrophic instability we witness. The star is constantly, violently shedding its own skin because the outward pressure of its own light is literally tearing it apart. The great eruption in the 1840s was not a gentle breeze. It was the star momentarily losing its grip entirely, blasting off 10 solar masses because the radiation pressure within finally overwhelmed every binding force. These stars do not quietly accept a limit, they rage against it, and their furious, eruptive lives are the direct consequence of physics pushed to the breaking point. The radiation that sculpts galaxies would utterly sterilize any nearby world. Yet the question remains, could planets even form in such a violent nursery? Theoretically, yes. A massive star is born from a vast disk of gas and dust, and where there is a disk, the basic ingredients for planet formation exist. The process would have to be incredibly fast, a race against time before the star's fierce ultraviolet light evaporates the disk or its stellar wind blows it all away. Any fledgling planets would need to coalesce quickly and then migrate to a much wider, safer orbit, far from the star's deadly embrace. Imagine a Jupiter-like gas giant, not orbiting at our solar system's placid pace, but circling a brilliant blue hypergiant from a distance of tens of billions of miles. The sky from such a world would be a permanent, searing daylight, dominated by a single, furious blue-white sun that appears as a tiny but unbearably bright disk. If the planet were in a multiple star system, the vista becomes even more surreal, with 2 or 3 colossal suns tracing impossible arcs across a sky never knowing darkness. But this is a borrowed paradise, a temporary beauty. The planet's fate is sealed by its star's short life. In just a few million years, that brilliant sun would swell into a red supergiant, potentially engulfing any inner worlds before culminating in a supernova that would vaporize any surviving outer planets. The very concept of a planet orbiting such a star feels like a cosmic paradox, a fragile marble circling a bomb. Yet there is another, even stranger possibility. After the supernova, the remaining debris disk around the newborn neutron star could, in theory, coalesce into a second generation of planets. These would be worlds forged from the ashes of a stellar explosion, orbiting a pulsar, a city-sized cinder blinking with deadly radiation. They would be airless, irradiated hellscapes, but they would exist, proving that planet formation is a tenacious process, capable of persisting even in the aftermath of stellar Armageddon. This layered structure is the star's final, desperate attempt to hold itself up. Deep inside a massive star in its last million years, you would find a cosmic onion of unimaginable heat and pressure. The outermost layer, the skin of this stellar onion, is a vast, relatively cool envelope of hydrogen, the original fuel of the star. Just beneath it, where temperatures climb into the tens of millions of degrees, a thin shell is actively fusing that hydrogen into helium. Dig deeper, and you enter a shell where helium nuclei are cramming together to form carbon. Each step inward is a descent into a hotter, more frantic hell. Below carbon, you find a shell fusing carbon into neon and magnesium. Deeper still, neon burns to form oxygen and more magnesium. Then oxygen atoms fuse into silicon and sulfur. At the very center, under temperatures exceeding 3 billion degrees, the final act plays out, silicon fusing into iron. Each of these layers is burning its specific fuel at a breakneck pace, each one operating at a higher temperature and lasting a shorter time than the one above it. The silicon burning shell, for instance, might exhaust itself in less than a day. This entire intricate, layered factory exists for one reason: to generate the outward pressure needed to support the star's immense weight. But it is a factory racing toward a dead end. The iron ash accumulating at the very core is the poison in the heart of the giant. It cannot be used as fuel. So the core grows silent and inert, while the shells above it burn ever faster to compensate, until the moment the final supportive layer winks out and the entire magnificent layered structure has nothing left to stand on. That silicon burning shell is the final sprint in a marathon that lasted millions of years. The star's core has become a frantic, layered machine, and the innermost layer is now fusing silicon into iron. This is the last possible reaction that releases energy. The temperature here soars past 3 billion degrees, a forge so hot that silicon nuclei are smashed together with such force they form nickel-56, a radioactive isotope that quickly decays into stable iron. But this process is breathtakingly brief. For a star 20 times the mass of our Sun, this entire silicon burning phase may last only a single Earth day. In that final 24 hours, the star consumes an amount of silicon equivalent to the mass of our entire planet. It is a desperate, furious consumption, the stellar equivalent of a machine revving its engine until the pistons melt. All the while, the iron ash accumulates at the very center, a dead weight that cannot be used as fuel. With every second, the core grows heavier and more inert. The outward pressure from this last violent fusion reaction is all that temporarily holds up the colossal weight of the star's outer layers, and then the silicon is gone. The final supportive flame winks out. In that instant, the core has nothing left to fight the relentless crush of gravity. What happens next is measured not in days or hours, but in milliseconds. The core, which has just spent a day in a frenzy of fusion, collapses from the size of Earth to the size of a city in less time than it takes for a nerve impulse to travel from your brain to your hand. This is the trigger. That catastrophic implosion unleashes the shockwave that tears the rest of the star apart, beginning the supernova we see from light years away. The star's entire life, a multimillion-year epic of cosmic construction, culminates in a single, frantic day of silicon burning, a final, brilliant flash before the darkness. The star's final breath becomes a nebula, a monument of light and color. After the supernova's blinding flash fades, what remains is not emptiness, but a rapidly expanding cloud of stellar debris, a supernova remnant. This is the star's ghost, a luminous echo of its violent death. Take the Crab Nebula, the remnant of a star whose explosion was witnessed on Earth in the year 1054. For almost 1,000 years, that cloud has been growing, its filaments of gas oxygen glowing green, hydrogen shining red, and sulfur in yellow hues stretching across 11 light-years of space. At its heart spins the star's collapsed core, a pulsar, a neutron star spinning 30 times per second, its fierce energy illuminating the entire nebula from within. These structures are far more than just beautiful cosmic tombstones. They are active, dynamic workshops. The shockwave from the explosion, still traveling at thousands of miles per second, plows through the interstellar medium like a cosmic snowplow. It sweeps up vast amounts of gas and dust, compressing it into thick, rippling walls. Within those compressed walls, pockets of gas become dense enough for gravity to take over once more. New protostars begin to coalesce, their birth triggered by the death of the old, and the material itself is the ultimate gift. The nebula is seeded with the heavy elements forged in the star's core, and during the supernova, iron, carbon, oxygen, silicon, and gold. This enriched gas mixes with the primordial hydrogen of space, raising its metallicity. When the next generation of stars and planets form from this recycled material, they will be born with the essential ingredients for rocky worlds and potentially life. So the cycle completes itself. A massive star lives a short, furious life, dies in a cataclysm that scatters the elements of creation, and from its ashes, in the beautiful, glowing nebulae it leaves behind, the seeds of new solar systems are sown. The universe's largest stars are not just destroyers, they are the ultimate recyclers, ensuring that every ending contains the blueprint for a new beginning. From the silent collapse of iron cores to the brilliant glow of supernova remnants, The story of these stellar titans is a testament to cosmic extremes. We have journeyed from their violent births in dense nebulae to their layered, frantic lives burning through fuel in a desperate race against gravity. We have seen how their furious winds sculpt galaxies, how their catastrophic deaths forge the very elements of life, and how their silent disappearances challenge our understanding of physics itself. These are not just distant points of light, they are the fundamental architects of the universe as we know it. Their unimaginable scale, their explosive power, and their profound generosity in death are all woven into the fabric of existence. To understand these giants is to understand our own origin story. The iron in our blood, the calcium in our bones, the oxygen we breathe, every atom in our bodies heavier than hydrogen was forged in the heart of a massive star that lived and died long before our sun was born. We are, in the most literal sense, the universe becoming aware of itself, built from the ashes of ancient stellar explosions. So the next time you look up at the night sky, remember that you are not just an observer of the cosmos, you are a product of its most magnificent and violent processes. You are stardust given thought and form. If this journey through the lives of the universe's most massive stars captivated you, please like this video and subscribe for more deep dives into cosmic mysteries. What is your favorite stellar wonder or unanswered question about the universe? Let us know in the comments